So we are going to discuss the most important technological aspects of semiconductors or the basics of semiconductors that are hugely being implied in the semiconductor industries such as integrated circuits or chips or microprocessors. So in terms of that, I will discuss the most pioneering feature of tailoring such semiconductors uh, in various technological applications and the basic physics of why the semiconductor industries are booming, uh, what our technology has reached today. So to start with, one could call a semiconductor a narrow band gap insulator in the sense that its energy gap between the highest field band and or the valence band and the lowest unfilled band, that is the conduction band, is typically of the order of 1 electron volt. The electrical conductivity of a semiconductor is consequently typically much less than that of a metal. The purity of a semiconductor is very important, and controlled doping is used to vary the electrical properties. Donor impurities are added to increase the number of electrons, and acceptors are added to increase the number of holes. Holes are a fictitious concept which are caused by the absence of electrons in states normally electron occupied, and it acts, or holes act, as positive charges. Donors are impurities that become positively ionized by contributing an electron to the conduction band, while acceptors become negatively ionized by accepting electrons from the valence band. The electrons and holes are thermally activated, and in a temperature range in which the charged carriers contributed by the impurities dominate, the semiconductor is said to be in the extrinsic temperature range. Otherwise, it is said to be uh, intrinsic. Over a certain temperature range, donors can add electrons to the conduction band and acceptors can add holes to the valence band as temperature is increased. These can cause the electrical resistivity to decrease with increasing temperature, giving a negative temperature coefficient or negative coefficient of resistance. This is to be contrasted with the opposite behavior as in case of metals, right? So for group 4 semiconductors such as silicon, germanium, etc., typical donors come from the column 5 of the periodic table, that is phosphorus, arsenic, antimony, and typical acceptors from column 3, that is boron, aluminium, gallium, indium, etc. Right? So to start with, the development of the transistor by Bardeen, Brattain, and Shockley in 1947, the technology of the semiconductors has exploded. With the creation of integrated circuits and chips, semiconductor devices have penetrated into long parts of our lives. The modern desktop or laptop computer would be unthinkable without microelectronic semiconductor devices, and so would a myriad of other devices. So a material which is insulating at low temperature but whose band gap Eg is small, that is zero point 0.1 electron volt to 2 electron volt, is called semiconductor. At finite temperature, a few electrons will be excited from the filled valence band to the empty conduction band. These electrons and holes, empty states in the valence band, are called holes, can carry current because the concentration of electrons in the conduction band varies like e to the power minus Eg upon 2 kBt. The conductivity increases with increasing temperature, right? So as I have discussed, these donor impurities are to increase the number of electrons and acceptors are to increase the number of holes. Then semiconductors tend to be bonded either tetrahedrally or covalently. Although binary semiconductors may have polar as well as covalent character. The simplest semiconductors are the nonpolar semiconductors from column 4 of the periodic table, silicon and germanium. Compound 3 to 5 semiconductors are represented by indium, either indium antimony INSB and gallium arsenide, while 2 to 6 semiconductors are represented by such as cadmium sulphide and cadmium selenide. As already alluded to, there are many applications of semiconductors. See, for example, includes diodes, transistors, solar cells, microwave generators, light emitting diodes, lasers, charged coupled devices, thermistors, strain gauges, and photoconductors. Semiconductor devices have been found to be highly economical because of their miniaturization and reliability. We will discuss several of these applications. The technology of semiconductors is highly developed but cannot be discussed in a full stretch within the syllabus. So let me restrict ourselves to the physics of semiconductors. Sometimes we have used that obviously uh, the band gap that we are mentioning is in between metals and insulators, express the energy between the top of the valence band and the bottom of the conduction band, and the band gap depends on the temperature and may slowly and linearly decrease with temperature. Sometimes we have used direct D and indirect I semiconductors. If conduction band minimum in energy and the valence band maximum occur at the same K or the wave vector value, one has a direct semiconductor, otherwise the semiconductor is indirect. Indirect and direct transitions are also uh, we'll discuss, and this is very useful for optical measurements of the band gap. Sometimes we have hired the density of states effective mass in the successive lectures to follow, and also certain kind of band structure, if time permits I will discuss, and the EK relations for the holes uh, I will shortly touch upon. Finally, mobility, which is the drift velocity per unit electric field, will be discussed, and the relative static dielectric constant is the permittivity over the permittivity of the vacuum. So the main objective of discussing this chapter is to discuss the basic physics of semiconductors, including the physics necessary for understanding semiconductor devices. Okay, so we'll start the discussing electrons and holes and their concentration and motion. So this is a typical table which shows the important properties of representative semiconductors such as silicon, germanium, okay, indium, antimony, gallium arsenide, cadmium selenide, and gallium nitride, which has I and D orientations. And I for indirect bandgap semiconductors with diamond structure, and this is for zinc blende structure for gallium arsenide, cadmium selenide, etc. And for gallium nitride is the Woodside structure. And the typical lattice constants are listed below. One cannot memorize it, but this is the typical order. And for Woodside, A and C is this. We have already in practice tried to measure the band gap of both silicon and germanium in our laboratories, that is 1.17 and 0.78 at 0K, and at room temperature it is about 1.12 and 0.66. Now, these values are already well studied, and these are the base indirect or direct semiconductors which are being used in photovoltaic cells or LEDs. So, brief about. So this is an important slide. Okay, let me show you. This is a very fantastic uh, slide. The scientist being awarded the Nobel Award for discovering in a way or another the transistor or semiconductor industry. So these are the scientists up to 2000 are being awarded for their groundbreaking discoveries related to semiconductors. Okay, so I think this slide will be plausible to be incorporated in my lectures. Okay, so these are some important crystal structures which are being important in the sense that the crystal structures that are important for semiconductor physics are listed. These are the rock salts, either such as lead sulphide or magnesium oxide, diamond structures such as carbon, silicon, germanium, zinc blend structures such as gallium arsenide, indium phosphide, and woodside structure for zinc oxide or gallium nitride structures. So the first one that I have showed is the rock salt structure, and the structure, sodium chloride structure, is very well known, consists of a FCC lattice with the period A and a diatomic base in which the chlorine atoms are positioned, right, at either 0, 0, 0, right, these the and sodium atoms are at half 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 A with a distance of root 3 A by 2. Materials that crystallize under normal conditions in the rock salt lattice are such as KCl, KBr, PBS, PBAC, PBTE, AGBr, MgOs, cadmium oxide, magnesium oxide, ALN, gallium nitride, and indium nitride undergo under high pressure a phase transition from the woodsite into the rock salt structure. So this is the NaCl structure. This is the cesium chloride structure. Cesium chloride structure consists of a simple cubic lattice similar as per the rock salt structure. The base consists of different atoms at 0, 0, 0 and half 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 A. Typical crystals with cesium chloride structure are TLBR, TLI, CUZN, or that I called brass, or ALNI, etc. So next I will discuss the diamond structure. Has the FCC lattice. The base consists of two identical atoms at 0, 0, 0 and 1/4, 1/4, 1/4 of A. Each atom has a tetrahedral configuration. The packing density is only about 0.34. The materials that crystallize in the diamond structures are carbon, silicon, germanium, and alpha SN. The diamond structure has an inversion center located between the two atoms of the base, that is 1/8, 1/8, 1/8 of A. The radii of the wave functions for the various group 4 elements increases with the order number and accordingly increases the lattice constant. So the second one, the B, is the zinc blend structure, and the such as zinc sulphide structure has a FCC lattice with a diatomic base. The metal A atom is at 0, 0, 0 and the non-metal B atom is at 1/4, 1/4, 1/4 of A. Thus the cation and the anion sublattices are shifted with respect to each other by a quarter of the body diagonal of the FCC lattice. The atoms are tetrahedrally coordinated. A zinc atom is bonded to four sulfide atoms and vice versa. However, no inversion center is present any longer. In the zinc blend structure, the stacking order of diatomic planes along the body diagonal is small a, capital A, small b, capital B, small c, capital C, again small a, capital A, so on and so forth. Many important compound semiconductors such as gallium arsenide, indium arsenide, aluminium arsenide, indium phosphide, gallium phosphide, and their alloys, but also the 2,6 compounds such as zinc sulfide, zinc selenide, zinc telluride, AGT, CDAC, and CDT crystallize in the zinc blend structure. Again, okay, this one the unit cell of the zinc blend structure with the indication of tetragonal symmetries. The position of the small white sphere is the tetrahedrally configured unoccupied positions of A, and the black are the B sublattices. These are the structure uh, with T in part of B. Okay, so fourfold coordinate materials that the zinc blend and woodsite typically undergo a phase transition into sixfold coordinate structures upon hydrostatic pressure. For gallium arsenide, under pressure. So woodsite structure is also called the hexagonal zinc sulfide structure because zinc sulfide has both modifications. It consists of a HCP lattice with a diatomic base. The C by A ratio typically deviates from the ideal value 8 by 3 to the power half, that is 1.63, and zinc atom is located at 0, 0, 0, the sulfide atom at 0, 0 root 3 by 8a. These corresponds to a shift of 3 by 8c along the c-axis. This factor is called the cell internal parameter u, that has the value u0 is equals to 3 by 8, that is 0.375 for the ideal woodsite structure. Many important semiconductors with large band gap crystallize in the woodsite structure such as gallium nitride, aluminium nitride, indium nitride, zinc oxide, silicon carbide, zinc sulfide, cadmium sulfide, and cadmium selenide. And this is the comparison of the tetrahedral bonds in the zinc blend and the woodsite structure. I is the inversion center, M is the symmetry plane. Okay, so these are the basics of few crystal structures. Now I will discuss the electron motion, or in a way calculation of electron and hole concentration in semiconductors. The calculation of carrier concentration based on typically number one is excitation of electrons from the valence to the conduction band, leaving holes in the valence band. Second one is the presence of impurity donors and acceptors or electrons. And the third one is charge neutrality. This discussion is important for electrical conductivity among other properties. So we start with a simple picture assuming a parabolic band structure of semiconductors involving conduction and valence band as shown in the figure. Okay. Here we talk about donor and acceptor impurities, and we are talking about shallow defects only. where the energy levels of the donors are just below the conduction band minimum and the acceptor just above the valence band, right? Maximum. So shallow defects will be discussed later. Uh, we limit ourselves to impurities that are sufficiently dilute that they form localized and discrete levels, and impurity bands can form where 4/3 pi a cube times n is nearly equals to 1, where a is the lattice constant and small n is the volume density of impurity atoms of a given type. The charge carrier population of the levels is governed by the Fermi function F. The Fermi function evaluated at the Fermi energy E is equals to mu is half, and we have assumed mu near the middle of the band, and the Fermi function is given by F E is equals to 1 upon exponential E minus mu divided by kt plus 1. Why E at E is equals to mu, that is half. If this numerator of exponential is 0, then e to the power 0 is equals to 1. Then in the denominator 1 plus 1 is equals to 2. Therefore this function becomes half. So in the figure, EC, right, this one is the energy of the bottom of the conduction band. EV, this one is the energy of the top of the valence band. ED is the donor state energy, right? Or the energy with electron, and in which case the donor is assumed to be neutral. EA is the acceptor state energy, which when it has 2 electrons and no holes is singly charged. Some typical donor and acceptor energies for column 4 semiconductors are 44 and 39 milli-electron volt for phosphorus and antimony in silicon, 46 and 160 milli-electron volt for boron and indium in silicon. We now evaluate expressions for the electron concentration in the conduction band and the hole concentration in the valence band. We assume that the non-degenerate case where energy E is E in the conduction band implies E minus V is far greater than the thermal energy kT. So this Fermi function becomes simply e to the power minus E minus mu divided by kT. If this exponential is far greater than 1, one can ignore 1, then the denominator in the numerator form becomes the negative of this exponential. We further assume a parabolic band so that E is equals to h cut square k square divided by twice m star plus EC, where m star is a constant which is the effective mass of electron. For such a case, we have shown the density of states given by 1 upon 2 pi square twice m star divided by h cut square to the power 3 by 2 root under E minus EC, and the number of electrons per unit volume in the conduction band is given by n is equals to EC to infinity, the density of states times the Fermi function what the dE, one can integrate it out. Why it is EC to infinity? Because this range is available. This is the empty conduction band. This is the lowest of the conduction band. So this comes from EC to infinity. Likewise for holes, one can integrate from minus infinity from that side to the upper limit minus EV, right? So the number of electrons per unit volume can be calculated as 2 times m star kT divided by 2 pi h cut square to the power 3 by 2 exponential mu minus EC divided by kT. For holes, we assume that energy is valence band energy minus h cut square k square divided by twice mh star, that is the effective mass for holes, which yields the density of states dH is equals to like the same manner for electron 1 upon 2 pi square twice mh star divided by h cut square root under EV minus E. The number of holes per state is FH is equals to 1 minus FE, that is 1 upon exponential mu minus e upon kt plus 1. Again, we make a non-degeneracy assumption and assume that my mu minus E is far greater than the thermal energy for E in the valence band. So the function, Fermi function for holes becomes exponential E minus mu by kT, and the number of holes per volume in the valence band is given by P is equals to minus infinity to EV, DHE, FHE, DE, from which we find P is equals to twice mh star kt divided by 2 pi h car square to the power 3 by 2 exponential ev minus mu upon kt. Since the density of states in the valence and conduction bands is essentially unmodified by the presence or absence of donors and acceptors, the equation for N and P are valid with or without donors or acceptors. So multiplying n and p, we find ni square, where ni assumed to be 2i's kt over 2 pi h car square to the power 3 by 2 m star mh star to the power 3 by 4 exponential minus eg upon 2i's kt, where eg is the ec minus ev, or is simple the band gap, and ni is the intrinsic or without donors or acceptors electron concentration. This equation is sometimes called the law of mass action and is generally true since it is independent of the chemical potential mu. So we have to calculate the number of electrons or donors and holes on acceptors. We use the basic theorem from the grand canonical ensemble from the book of Ashcroft-Marvin, that this average is nothing but sum upon j nj exponential minus beta ej minus mu nj divided by summation except nj, this exponential part, or the exponential of minus beta ej minus mu nj, where beta is equals to 1 upon kt, and this left hand part are the mean number of electrons in a system with states j, with energy ej, and number of electrons nj. So this is a model for energy and degeneracy of donors, where the first column is the number of electrons, energy, and degeneracy of state. Ng is equals to 0 means En 0, energy 0, and degeneracy 1. Ng is equals to 1 means the energy Ed, the donor energy, and the degeneracy is 2. When Nj is equals to 2, energy tending to infinite, and the degeneracy we have to neglect as it is too improbable, right? So we are considering a model of a donor level that is doubly degenerate in a single particle model, and it is possible to have other models for donors and acceptors. There are basically three cases to look at in this table, noting that when we sum over all states, we must include the degeneracy factors. For the mean number of electrons on a state J is defined by the mean n is equals to 1 to exponential minus beta ed minus mu divided by 1 plus 2 exponential minus beta ed minus mu, or n becomes 1 upon half exponential minus beta ed minus mu plus 1, that is small nd divided by capital Nd, where small nd is the number of electrons per volume on donor atoms and capital Nd is the number of donor atoms per volume. For the acceptor case, our model is given in another table, where this is number of electrons, number of holes, energy, and degeneracy. When the electrons are 0, that is absence of electron means 2 holes. The energy is very large, degeneracy we can neglect. This is 1 1, energy is 0, degeneracy is 2 2 0, energy is acceptor state energy, and degeneracy is 1. So the number of electrons per acceptor level of the type defined in the previous table as 1 2 exponential minus beta minus mu, 2 1 exponential minus beta ea minus 2 mu divided by 2 exponential beta mu plus exponential minus beta ea minus 2 mu, and one can written as exponential beta mu minus Ea plus 1 divided by half exponential beta mu minus Ea plus 1. Now the average number of electrons plus the average number of holes associated with the acceptor level is 2, and simply the average n plus average p is equals to 2. We just find this p as Pa by Na, which is 1 divided by half exponential beta mu minus Ea plus 1, where this Pa is the number of holes per volume on acceptor atoms and capital Na is the number of acceptor atoms per volume. So this is a typical sketch of variation of Fermi energy or chemical potential mu with temperature for Na is 0 and Nd is greater than 0. This type of behavior are being maintained. This is the energy state for the lowest of the conduction band. This is the mu intrinsic. This is the donor level energy gap, and mu looks like that. And as this increases, this tends to the intrinsic limit. And the energy uh, Fermi function and the defect level is plotted from in the temperature inverse with the ln of n, which follows this type of behavior. This is a plateau or flat region, and from here the slope defines the band gap energy divided by 2 with a negative sign. This is the intrinsic region. This plateau is basically called the exhaustion region, where donors completely ionized and N becomes Nd. This slope gives us the negative value of Ec minus Ed divided by 2, and at the last part this slope is simply minus Ec minus Ed, right? So from that we will discuss the equation of motion of electrons in energy band. This is nothing new. We start by discussing the dynamics of wave packets describing electrons. We need to do this in order to discuss properties of semiconductors such as the Hall effect, electrical conductivity, cyclotron resonance, and others. In order to think of the motion of charge, we need to think of the charge being transported by the wave packets, right? The three-dimensional result using free electron wave packets can be written as V is equals to nothing but 1 upon h cut this gradient over k ek. This result we now discuss is appropriate even if the wave packets are built out of Bloch waves. Now, let a Bloch state be represented as psi nk is equals to unk is a function of r times the plane wave function, that is e to the power I k dot r, where small n is the band index and unk is periodic in the space lattice. With the Hamiltonian h is equals to 1 upon twice m grad h cut by I grad whole thing square plus Vr, where Vr is periodic in nature, which implies psi upon a Hamiltonian upon psi nk is equals to enk psi nk, and we can show hk this has to be a suffix here. psi hk unk is equals to enk unk, right? Here a k is missing. hk unk is equals to enk unk, where hk is simply h cut square divided by twice m grad divided by I plus k whole thing square plus pr. Note hk plus q operating upon unk plus q is enk plus q unk plus q, and to first order in q, this becomes hk plus q is equals to hk plus h cut square by mq dot 1 upon I grad plus k, and to first order ek en k plus q is equals to enk plus q dot gradient of enk. Also by first order perturbation theory, enk plus q is equals to enk plus integration unk h cut square by m q dot 1 upon I grad plus k unk dv. From this we can conclude gradient over k enk is equals to integration unk h cut square by m 1 upon I grad plus k unk dv, which is h cut comes out of the integration psi nk h cut by mi grad psi nk dv, which is h cut within bracket within the psi nk times h cut by I grad is nothing but the momentum divided by mass ket psi nk. So we define this as the velocity, as this is the expectation value of p by m, or the velocity, and then b equals to the average velocity of the electron in the Bloch state nk. So we find velocity is 1 upon hk gradient over k enk. Note that v is a constant velocity for a given k. We interpret this as meaning that a Bloch electron in a periodic crystal is not scattered. Note also that we should use a packet of Bloch waves to describe the motion of electrons. Thus, we should average this result over a set of states picked at T. It can also be shown is the appropriate velocity of such a packet of waves. Now we apply external fields and ask what is the effect of these external fields on the electrons. In particular, what is the effect on the electrons if they are already in a periodic potential? In an external force, F external, right, acts on the electron during a time interval delta t, it produces a change in energy given by delta E is equals to F external times delta x, that is F group velocity times delta t. And substituting the value of V from which delta E can be written as F external times 1 upon h cut delta E delta k times delta t. Now cancelling delta E from both sides, one can write F external is equals to h cut delta k delta t. This one, and the three-dimensional result may formally be obtained by analogy to the above is F external is equals to h cut dk dt. In general, F is the external force, and if E and V are the electric and magnetic forces, magnetic fields, then h cut dk dt is the external force, and right hand is the Lorentz force, that is the charge times charge means electronic charge is minus E times E the electric field plus V cross B. This result is often called the acceleration problem in K space. We next introduce the concept of effective mass. In one dimension, by taking the time derivative of the group velocity, we obtain dv dt is nothing but 1 upon h cut in a chain rule d2e dk2 times dk dt. That is 1 upon h cut square d2e dk2 f external. Defining the effective mass, so F external is nothing but m star dv dt, mass times acceleration, right? So we have m star is equals to h cut square divided by d2e dk2, and in 3 dimension this becomes 1 upon m star alpha beta is equals to 1 upon h cut square del 2e del k alpha del k beta for the anisotropic matter or material. So notice in the free electron case where E is h cut square k square divided by twice m, this 1 upon m star alpha beta becomes delta alpha beta divided by m. One can easily prove the effective mass of electron and effective mass of holes are perfectly same with a negative sign, right? So I will now discuss okay uh, as the temperature goes high, from this is 0 degree, this is 300 degree, and this x-axis is for temperature in degree Kelvin. As the temperature goes up, the Fermi level of the n-type semiconductor falls steadily in the energy gap, and the Fermi level in a p-type semiconductor rises in same proportion. Above the temperature Ti, at which n nearly equals to ni, so Ti is simply at the temperature at which n is nearly proportional to ni, marks the transition to intrinsic conductivity. Ti is higher for large forbidden gap and the impurity concentration. It ranges from 450K or so. So above this Ti, the Fermi levels of these semiconductors coincide with that of the intrinsic semiconductor, like in the same way, this falls and this rise enough. So EF minus P material, EF minus M material, and finally march to the intrinsic Fermi level. Therefore, we have to discuss this curve as coincide with that of the intrinsic semiconductor, with itself vary slightly with temperature. Also, their carrier concentrations become identical to that of intrinsic semiconductor. Variation of the Fermi level in impurity materials as a function of temperature is illustrated in this figure. So this figure shows the temperature dependence of Fermi level in N and P materials. Electron and hole masses are assumed to be equal. So depending upon that, we'll discuss a problem here. So the problem is in a p-type semiconductor, the Fermi level lies 0.4 electron volt above the valence band. If the concentration of the acceptor atom is tripled, and Kt is equals to 0.03 electron volt, find the new position of the Fermi level. So given p-type semiconductors, the EF minus EV is equals to 0.4 electron volt, Na prime is equals to tripled as 3 times Na, and Kt is equals to 0.03 electron volt. So what is the value of EF prime minus EV? So this is the solution. For a p-type semiconductor, the hole density is given by p is equals to nothing but Na, which is Nv exponential minus Ef minus Ev divided by Kt, and p prime is equals to Na prime, which is tripled 3 times Na, that is Nv exponential minus Ef prime minus Ev divided by Kt. And comparing these two equations and removing exponential term, we have EF prime minus EV is equals to EF minus EV minus KT ln 3, which is 0.4 minus 0.03 times 1.098, that is 0.4 minus 0.032, which finally turns out to be 0.367 electron volt. Now, another important for semiconductors are the charge and the heat energy, which can be transported through the semiconductor in the presence of appropriate forces. Such a force can be an electric field or a temperature gradient. Both transport phenomena are coupled since electrons can transport energy and charge through the crystal. First, we will treat the charge transport. Both, as I have mentioned, the charge and heat energy can be transported through the semiconductor, and both transport phenomena are coupled since electrons can transport energy and charge through the crystal. We will treat the charge transport as a consequence of a gradient in the Fermi level, then the heat transport upon temperature gradient, and finally the coupled system, which are effective in Peltier and Seebeck effects. Practically all important semiconductor devices are based on the transport of charge, such as diode, transistor, photodetector, solar cell, then laser. Carriers move in the semiconductor driven by a gradient in the Fermi energy, and we distinguish either by drift, which is a consequence of an electrical charge E, and second one is diffusion as a consequence of a concentration gradient, either gradient of N or gradient of P. So inhomogeneous semiconductors for which the position of the band edges is a function of position, another force occurs. These will not be treated here in this discussion, and it will be included as an additional or internal electrical field. Many semiconductor properties, such as the carrier concentration and the band gap, depend on the temperature. Thus, device properties will also depend on temperature. During operation of a device, typically heat is generated, that is by Joule heating due to finite resistivity. This heat leads to an increase of the device temperature that subsequently alters the device performance, mostly for the O's. Ultimately, the device can be destroyed. Thus, cooling of the device, in particular of the active area of the device, is essential. Mostly, the thermal management of device heating limits the achievable performance or the lifetime of the device. In high power devices, quite high energy densities can occur, and that is the facet of a high power semiconductor laser has to withstand an energy density beyond 10 megawatt per centimeter square. Now, depending upon that, we discuss the conductivity under the influence of an electrical field. Electric field, the electrons accelerate according to force is equal to mass times acceleration, that is dvdt, which is h cut dkdt, which is charge times the electric field, that is the electronic charge minus E times electric field. And Q denotes the general charge, while E is the positive elementary charge. After the time interval delta t, the k vector of all conduction electrons and the center of the Fermi sphere has the shifted by delta k, where delta k is equals to minus E delta T divided by H cut. In the absence of scattering processes, this goes on further. The regime called the ballistic transport. In a band structure, the electron will perform a closed cycle as indicated in this figure. This is the schematic representation of a Bloch oscillation. Each such motion is called the Bloch oscillation, and however, in a bulk crystal, the period T of such an oscillation is EET divided by H cut, that is 2 pi by A0, is the order of 10 to the power minus 10 second for electric field E is equals to 10 to the power 4 volt per centimeter. This time is much longer than a typical scattering time, which is 10 to the power minus 14 second or so. Thus, in bulk material, the Bloch electron cannot reach the zone boundary. This is the dotted curve. However, in artificial superlattices with larger periodicity at about 10 nanometer, the high electric field at about 10 to the power 6 volt per centimeter, and high quality reduced collision time, such motion is possible. We note that in the absence of scattering, electrons can perform a periodic oscillation in a magnetic field, which are called the cyclotron motion. In a real semiconductor, at finite temperatures, impurities, phonons, and defects will contribute to scattering. In the relaxation time approximation, it is assumed that probability for a scattering event similar to friction is proportional to the average carrier velocity. The average relaxation time tau is introduced via an additional term v dot is equals to minus v upon tau that sums up all scattering events. Thus, the maximum velocity that can be reached in a static electric field is given by steady state velocity v is equals to minus e capital E tau divided by m star, and the current density per unit area is then linear in the field that is fulfills Ohm's law, that is J is equals to NQV, which is N is square E tau divided by m star, and this is sigma E. The conductivity sigma in the relaxation time approximation is given by sigma is 1 upon rho, that is N square tau by m star, and the specific resistivity is the inverse of the conductivity. Metals have a high conductivity, that is for copper at room temperature, this sigma has the value of 5.8 into 10 to the power 5 ohm inverse centimeter inverse. At low temperatures such as 4 Kelvin, the conductivity is even a factor of 10 to the power 5 higher. The mean free path is then 5 millimeter and thus susceptible to the sample geometry, while at room temperature the mean free path is only 30 nanometer. In semiconductors, the carrier concentration depends strongly on the temperature. At zero temperature, the conductivity is 0. Also, the scattering process and thus the relaxation time constant exhibit a temperature dependence. So another important aspect is mobility. The mobility is defined in scalar terms is V upon epsilon. By definition, it is a negative number for electrons and positive for holes. However, the numerical value is usually given as a positive number for both carrier types. In an intrinsic semiconductor, the mobility is determined by the scattering with phonons. Further scattering is introduced by impurities, defects, or alloy disorder. The conductivity is given as sigma is equals to Q times N concentration times mu mobility for each carrier type. The mobility in the relaxation time approximation is mu is equals to Q tau by m star. Thus, in the presence of both electrons and holes, sigma is equals to minus En mu n plus Ep mu p, where mu n and mu p are the mobilities for electrons and holes respectively. In the relaxation time approximation, these are given by mu n is equals to minus E tau n divided by m star, and mu p is equals to E tau p divided by mp star. As a unit, usually centimeter square per volt second is used, while copper at room temperature has a mobility of 35 centimeter square per volt second. Semiconductors can have much higher values. In two-dimensional electron cases, the mobility can reach several 10 to the power 7 centimeter square per volt second at low temperature. In bulk semiconductors with small band gap, high electron mobility is caused by its small effective mass. And this is a table of mobilities in units of centimeter square per volt second for electrons and holes at room temperature for various semiconductors are listed below. So one can have a high estimation what is the value for the mobility for electrons and holes.